Okay, so hi everyone. Today we're going to solve this problem, that is LeetCode 295 find median from data stream. It's a very good problem and it's a hard problem. Although I will say that it's not like a hard problem, but yeah, it is of good level. I will say that it's better than the medium level problem. So and it has a very decent like to dislike ratio. So let's start this problem. So first of all, what is the median of the so first of all, this problem conveys the message of median. So what is the median? So if you have this element 2, 3, 4, 5, so this is an even length array. So this is an even length array. If it's an even length array, then the two middle elements, then we need to take two middle elements and we need to take the average of them, and that will be 7 by 2, and that is 3.5, right? But if it is not a even length array, then it's an odd length array, which means 2, 3, 5, and in this case the middle element will be the median, that is 3. So this is the first line, and then we need to understand what does this add num function does. So let's say you have a data structure, right, and you are adding these numbers 1, 6, 7, 3, right, and whenever I call the query to find the median, then you should be able to return that this data structure should be able to return me the median. And how to return the median? There's one condition. So the first condition is that it has to be a middle element. If it's a odd sized array, it has to be a middle element. But if it is not an odd sized array, if it's a even sized array, then you need to take the average of two middle elements. And in this case, it's an even sized array. But there's another major condition, and that is the list has to be sorted, as it says in the question that ordered integer list, which means the list has to be sorted. So the sorted list will be 1, 3, 6, 7. In this list there are two middle elements, that is 3 and 6. So 3 plus 6 by 2, this is equal to 9 by 2, this is equal to 4.5. This is your median for this particular answer. So this is a problem. How we can do it? Now there are multiple ways of doing it. I think only two ways which came to my mind. So the first one is to use the basic approach of storing these elements in the array. So you have 1, 6, 7 and 3, and whenever we call the median, we sort the array up. So after sorting, this array will become 1, 3, 6, 7, and then we can return these two middle elements and the answer will be 4.5. Now what is the time complexity of this approach? So basically in the worst case, so let's say you have an element and then you're finding the median, you have an element, then you're finding the median, you have another element, you're finding the median, then you have another element, you're finding the median. In this type, -1 and you're finding the median, and so on. So this is the worst case, when you are finding median again and again, and you can see the median will be called, if there are n calls made, the median will be called n by 2, right, and the count of numbers will be n by 2, which means that you will be sorting these numbers on n by 2 basis, which means it's an n square, n into n log n algorithm, which is n square log n algorithm, which means it's an n square algorithm, and the number of calls that could be made is equal to 10 raised to the power 5, which means it won't be running in n square time. So we need to optimize it. How to optimize it? Use priority queue. Not just one priority queue, we will use two priority queue, and I will tell you why we are using two priority queues. The one will be a max heap and the other one will be a min heap. So in a sorted array 1, 2, 3, 5, 4, right? So first of all, this is not a sorted array. 4, 5, this is a sorted array. In this sorted array, you can easily observe that there is a half, right? So let's say we have only 4 elements. So let's say this is the sorted array and these are the first half, this is the second half. What are these halves? These halves are basically a max heap, right? Because it's a sorted in increasing order, so the last element of this heap or the priority queue will always be greater, and the elements that are stored on back of this from down towards the bottom of the priority queue will always be smaller than the above ones, which means it's a max heap, and this is nothing but a min heap, right? I think it perfectly makes sense. So now we have an option, rather than to create a max heap and min heap from array, why shouldn't we insert elements accordingly into these max heaps, so that when we are finding the middle element, we can instantly get them in, even in also in a constant time. So how to do so? So we are given these numbers, then we are finding a random value, right? So we are given 6, nothing is there in the max heap, we return 6. 7 is greater than max heap, 7 is greater than the top element of the max heap, so we will return 7 in in this one, because 7 is greater than 6, so it should be returned in the min heap, and this is a max heap. And now we have 1 is smaller than 6, so 1 should be stored in the max heap, which means 1 will be here. And now we have 2. Now 2 is smaller than 6, which means 2 should be inserted here, which means it will be like 1, 2 and 6. But this is a false case. So let's say after this time I call a random function. When I call a random function, I should be able to return the middle element. So the array will look like this, right? And this should be the max heap and this should be the min heap. In that case, I can return the top element of the max heap and top element of the min heap, and their average will be my answer, right? In this case, it should be 4. But in this case, we cannot find 4 because 6 plus 7 is going to be 13, and 13 by 2 is 6.5, which is not the answer. Answer should be 4. So how to do this? We will say that the max heap size, if the max heap size is greater than the min heap size plus 1, then it's a false condition, which means the max heap have more elements and one more element, and this element should be pushed into the min heap. So this is the case where we are encountering this problem, and now we are going to fix this by popping 6 out of the stack and pushing 6 into the stack, into the priority queue. Now we have 1, 2 and 7, 6. Now this looks exactly like this sorted array, and now we can return the median, and the median will be 6 and 7, because this is a min heap, so 6 should be at the top, and this the median will be 2 plus 6, that is 8. 8 divided by 2 is 4, so 4 is the answer, and it's working perfectly fine, right? Now we have 5. So 5 is smaller than 6 and it is greater than 2, so I will insert 5 here. Now we have 4. Now 4 is smaller than 6. Let's say at this point we have 9. Let's say at this point we have 8 and 9, right? So now we have 8. So 8 is greater than 5. So I will push 8 here, and this is where I will store 8. And now we have 9. Now 9 is greater, no, let's say we have 10 also. Now we have 9. 9 is greater than 5, so it should be pushed here as well. So I will have 9 here, right? And then we have 10. Now 10 is greater than 5 also, so we will push 10 here as well. But this is a problem. This subarray does not have the consistent frequency of the elements. And the condition that I will have now is the minimum has the greater size than the max element plus 1, which means the minimum has the size of 5 and maximum has the size of 3 plus 1, that is 4. And 5 is greater than 4. Yes, the condition is violated. So because of that, this is the perfect example of this condition, and because of that we need to push the top element of the min heap into the max heap. So this will be like this, and now you can see there are 4 elements. They are equally distributed, which means now we can return the random, and the random will be 6 plus 7, that is 6 by 6.5, right? Now there's another case, like for example, let's say we have not inserted 10 but we have asked for the random. Now 10 is not there, right? And 6 is here. Now what? So we have 1, 2, 5 and we have 6, 7, 8. Now this is a perfect representation of 1, 2, 5 and we have 6, 7, 8 and 9. So this is the middle element. Then we will return that element as the median from the priority queue which has greater size. In this case min heap has greater size, so 6 is my answer. The top element of min heap is my answer, and that's it, right? So, and let's say for a case where we have 6 at this side, in that case I will return max heap as the top element of the max heap as my answer, as the median, right? Because this is nothing but this similar case. So I think this makes sense. So every element will be inserted in a log n time. So this will be, and for every element, for n element we will take log n time, and retrieval of the median element will be done in constant time. So it's a basically n log n algorithm. So yeah, it is an optimization over the n square one, that's for sure. So that's why this algorithm is preferred. Now let's write the code. So we have a priority queue. So we have a priority queue of int, and this is a max heap. Then we have a priority queue of int, and this is a min heap, so we need to add vector int. Basically this is just a syntax, greater int, and this is a min heap, right? Yes, the constructor can be empty. We are not using this constructor at any point, so this can be empty. Now add num. So if max heap is empty, and so if max heap is empty, then simply insert the element into the max heap. So max heap dot push this num value, right? So other thing is, if max heap is not empty, fine. Now we need to compare if num value is smaller than or equal to the max heap dot top value, right? In that case, if it is smaller than or equal to max heap dot top value, then it means the element is belongs to the first half, and the owner of the first half was a max heap first half, and this is the second half. Okay, yes. Yeah, so now what you will do is you will have max heap, you will give that element to the max heap dot push num, right? Now else condition is, if the element is greater than the top element of the max heap, then it should be inserted in the min heap, right? Now after this insertion we need to, so this is the um, insertion based on the value or based on the element rank in the sorted array, right? Now we need to take care of the size, maintain the consistent size of the two halves of the sorted array, right? And to do so, what we will do is, we have these conditions that I have told you earlier. So one is max heap elements, max heap dot size should be greater than min heap dot size, right? So if we have max heap dot size greater than min heap dot size, which means max heap has an extra value, so min heap will be given that value. So min heap dot push the max heap dot top value, and max heap will not have that value any longer, so it will be popped out. And else if, or just if condition again, and that is if min heap dot size is greater than max heap dot size, sorry, this condition is min plus 1, right? So min heap size plus 1, and in this case it should be plus 1. So if this is the case, then then max heap should have that value from the min heap, from the top of the min heap, and and min heap should remove that value or pop that value out of it, pop, right? So I think now we are also maintaining the size of the two halves, and now we need to return the median. So median will be returned in this case if the max heap dot size is equal to min heap dot size, which means both of the elements have equal sizes. Then we need to return the average of the, then we need to return the average of their middle elements. So that will be max heap dot top plus min heap dot top divided by 2.0, right? Otherwise, now in this case they don't have equal values, so any priority queue which is having more value will have the top value as its middle, as the middle element of the whole array, which means if max heap dot size is greater than min heap dot size, right? If this is the case, then max heap dot top is the element, otherwise min heap dot top is the element. So yeah, this is the code, and let's see if this will pass all the test cases. I mean, it will pass because I have okay, this should be, yeah, I mean it will pass because I have solved it earlier. So okay, that's embarrassing, but it's fine. Let's see what is the problem. So we have max heap dot top, we have min heap dot top, and we are following this condition that min heap size Okay, that's fine. Now num value is smaller than or equal to max heap dot top, then it should be in the max heap. If max heap is empty, then they should be returned inserted into the max heap. Makes perfect sense. So what could be the issue? Let's see. So if max heap dot size is greater than min heap dot size, then we need to return max heap dot top. This would be the element. This would be the middlemost element. And if min heap value is greater, then we return this one. Okay, so we are adding these nums. Max heap dot push. Okay, so now we need to call return at this case. This should return. This shouldn't follow these conditions anymore, because if the heap is empty, because this condition will be called again and again. And I think now it will. Okay, yeah, it will run fine, and it is not performing well. So let's see what is the faster solution. Wow, great, we are using the same thing. Okay, yeah, we are doing the same thing and the complexity is same. I don't understand what is going on here. Anyway, so let's just get along with it, and space wise it's performing good. And yeah, so this is the solution, and the time complexity of this function of add num will be equal to order of n log n, and this is a constant time function, so constant, and the time complexity for this will be n log n, as explained earlier, order of n log n, right? So this is it, guys. If you want to see the source code yourself, then you can find it in the description below. Otherwise, yeah, so that's it. Thanks for watching. Have a good day.